Welcome to today's webinar, Essential Capabilities of an IoT Cloud Platform. Our presenter today is Ian Massingham. He's a Chief Evangelist with EMEA and AWS. Again, you can use the Q&A pod on your screen at any time to ask those questions. Now, Ian, welcome. The floor is yours.
Thank you, and good evening, everyone. Good evening from the UK, where I'm located. Good afternoon if you're based in the US, of course. And I want to welcome you to this evening's webinar. My name's Ian. I'm a technology evangelist with Amazon Web Services based in Europe. I'm going to be your host for this session today. And we're going to be focusing on the core capabilities, the essential capabilities of an IoT cloud platform in today's webinar. So we kick off with a quick discussion of, I'm on my final slide. Sorry about this. So we'll kick off with a quick discussion of the core of what AWS IoT is, some early use cases, and then we'll move on to talk about those essential capabilities in some detail. So is AWS, which we launched in November 2015 at AWS reInvent. But AWS was actually used extensively prior to the launch of AWS IoT for connected device and Internet of Things applications. It was a popular early use case for AWS actually, and we had significant customers using AWS for this type of service before we launched our IoT service proper back in November, December 2015, as I said. Customers like Tile, you may be familiar with this product. It's a Bluetooth low energy tracker which has an accompanying mobile app which can be used to locate products in the physical world using the mobile application that they provide. I use that to great effect in my home for tagging all of the items that my 7- and 5-year-old like to lose around the house. I can find them audibly using the tiles that are stuck onto them. It's a pretty cool product that's built on AWS. In the regulated sector with Philips, Philips connect their medical imaging devices to the AWS cloud. So they turn X-ray machines and CAT scanners into large-scale medical connected devices, and they use this to modernize the care pathway for patients in clinical care scenarios such as trauma centers and patients that are undergoing oncology care, for example. So they turn their scanners into IoT devices. And then again in the consumer products area with Sonos, with the extremely popular connected speaker product that Sonos have. The control plane for Sonos is built in the AWS cloud and has been for quite some time. So we had these early use cases, these early adopters that were making use of AWS for this particular class of applications. And we were repeatedly asked by customers to simplify the process, to streamline the process of enabling AWS customers to build these types of applications, these connected device applications. And the step that we took in the first instance to do this was to launch the AWS IoT service back, as I said, in October 2015 we announced it, and we made the service generally available in December the same year, just a couple of months later. And the intent here was to make it simple for developers to securely connect devices at any scale, to create applications and interact with other devices, so to simplify the process of making it possible for developers to build IoT apps in the AWS cloud. And to do that, we focused on several core capabilities, and we're going to spend the rest of the session today discussing these capabilities in more detail. They are structured into a platform, and you will see this slide repeatedly throughout the course of today's session. It's a very useful way to think about the different components of the AWS IoT service, how they integrate together, and how you can put them to work to build applications of this type. Since we launched the service back in 2015, we've seen a real explosion in usage of AWS for this particular application class, and actually it's really broadened out now. We have customers that are building consumer products. We have customers like Karsha. They are an industrial manufacturer of washing equipment, and they have modernized their business model using IoT as a mechanism for metering usage of large-scale shared cleaning equipment. So if you're washing an aircraft at an airport over here in Europe, say at Frankfurt or in Munich perhaps, you'll find that there are large Karsha pressure washers sitting around on the tarmac that used to clean down aircraft. Customers, the airlines themselves, are charged on the basis of the number of run hours of this equipment that they consume. And that's enabled using the AWS platform, AWS IoT, to create a consumption-based model for that heavy industrial equipment. At the other end of the spectrum, we've got brand new startups like DoorDeck, you can see bottom left. It's a simple product for domestic home security, locking and unlocking access points, doorways, using smartphones. And it's built, once again, on AWS IoT. So no matter how big your organization is, if you're creating IoT products, AWS is a really good place to do that. So topics for the session. We're going to take a look at security. We'll take a look at device SDKs, communications mechanisms, how to process and act on device data, storing and querying device metadata attributes. We'll take a look at state caching and asynchronous device updates with the device shadow. And then lastly, we'll take a quick look at a service that's in preview from AWS to enable edge computing capabilities within IoT applications. So we often talk about security as job zero at AWS. It's a little bit of an internal joke within Amazon Web Services, actually. One of the reasons for that is you can't launch a service at Amazon Web Services if you don't build three fundamental capabilities into the service: security, reliability, and scalability. And you can't get through our gates for launch without meeting certain security criteria that are set within AWS for all new services that we create. So it is really job zero for service owners here at AWS in creating new services. They have to be secure. Unfortunately, that is a little bit at odds with the general perception of security in Internet of Things applications. There have been some notable, pretty high-profile examples of poor security architecture, poor security practice in IoT products that have been created and sold actually at quite significant scale. This has led to some recent adverse press coverage. You can see here from last year, DDoS attack, which was staged using webcams and other poorly protected IoT devices as a launch platform for an attack which had some pretty significant consequences. The situation in the third quarter of last year was so bad that lax IoT security became a meme in its own right. Okay, but the fact is it doesn't have to be like that. The reason that it is like that is applications are built that do not have a centralized control plane with strong identity. The manufacturers of these devices, of these products, will encourage customers to directly expose endpoints for the products on the public internet by doing things like setting up port forwarding on domestic firewalls, and you end up with large-scale situations where large numbers of devices have vulnerabilities which are later discovered. Those vulnerabilities can be discovered automatically by bad actors using tools that are available to search for insecure IoT endpoints. They can take over these devices, and it's all born out of the desire to create low-cost products that can be controlled by customers, by users, wherever they happen to be on the internet. So when you go outside that firewall, the device is still contactable and still accessible. Challenge there, of course, is the bad actors can automate the process of discovering, subverting, and taking control of these poorly secured endpoints. Which takes you to this situation, answering the question really, where do botnets come from? Well, it's mass scale hijacking, taking over of these poorly secured, poorly configured endpoints. But as I said earlier, it doesn't have to be that way. It is possible to build secure IoT applications, and you can do that by decoupling the control plane from the devices using a cloud-based IoT platform and focusing on identity and enabling secure communication with those things. So when you go out onto the public internet and you want to control your IP camera or your automated robotic vacuum cleaner or whatever your device is, you're using strong security principles to authorize and authenticate that connection. And you'll notice that the connectivity from the device to the control plane is unidirectional. So the device communicates with the control plane to get its instructions. There is no need to directly expose the device endpoint with a publicly routable address and make that vulnerable to any kind of attack. This is a model that is used quite extensively in building secure communications with things. And one of the key capabilities, one of the most important capabilities actually in selecting an IoT platform is choosing a platform that has its security house in order, that has the right identity and security management controls in place to enable you to build IoT applications that have these fundamental characteristics and meet the security bar that is necessary for this kind of application. It's quite different actually from web-based applications. In web-based applications, which you can see represented at the top here, you want to allow anonymous users to connect to your application, and this uses per session key generation, as you'll probably know. So setting up a new TLS SSL connection to a web server endpoint for HTTPS, well, the client does not have a private key, a certificate, when they start the connection. The server does, and the client is interested in the server's identity, but the server is not interested in the client's identity. Authentication takes place at the application layer. So you can tolerate and accept anonymous clients in that web server use case. In the IoT use case, that's not really a great idea. You want to have strong identity. You want to have public key cryptography in play bidirectionally so that the identity of both ends of the connection is known, and you can trust the endpoint that you're communicating with. So in the AWS model, we actually support a couple of different cryptographic options here. We're using asymmetric cryptography, public-private key cryptography in both cases, either with RSA keys using key lengths that you can see here, or using elliptical curve cryptography, which enables you to use shorter key lengths for an equivalent level of cryptographic protection. Device overhead in dealing with the cryptographic operations is reduced in comparison to using RSA keys. Still get the benefits of asymmetric cryptography with differing keys on each end of the connection, public and private keys, but using the ECC cryptography, you're using shorter keys, and that can reduce power overhead in the devices by reducing the level of computation that's required for crypt and decrypt operations. If you want to read more about that, it's probably beyond the scope of this webinar to go into it in much more detail. Grab the slides, which you can do, and follow the link at the bottom of the slide here, and you'll find more information about ECC cryptography with AWS IoT, which was a release that we did last year. Communicating with non-things, with humans. This is about the control plane interface, and there are some differences between the device connectivity, where we use TLS, mutual certificate-based authentication, predominantly over MQTT for power efficiency purposes. Confidentiality is covered with TLS, transport layer security encryption. It's likely that the devices are more powerful that you're going to be using there. Smartphones, browsers, there's plenty of CPU horsepower on hand in those devices. Here you can continue to use HTTPS, you can use AWS API keys, and you can deal with key generation each time you create a connection on the human control plane. The devices, as I've said, generally more powerful. So that's the split in the different models that we would use there. And then on thing identity, well, this is where your X509 certificates, your certificate authority or CAs come into play, and you get this trust hierarchy that can be established. And with that trust hierarchy, you can take control of generating your own cryptographic materials, creating and signing your own X509 certificates. You can establish a trust relationship between the certificate authority that you run and the AWS IoT service. And you can use that for features like register device on first use, which we're going to talk about a little bit later. So you have several different options with AWS IoT as to how you manage the CA, how you manage the certificate authority, whether you allow us to choose to take that on yourself, mostly private key pairs, and autonomously create X509 certificates and take advantage of that register on first use that I just mentioned a few minutes ago. So once you know who it is you're dealing with, or in the case of IoT, what it is you're dealing with, the things that you're talking to, their identity, how can you put that to work to implement a principle of least privilege and build highly secure IoT applications? Well, the answer there is fine-grained authentication. And this is relevant in the data plane, which you can see here, and also in the control plane. So the data plane will be messages flowing through that device gateway over the MQTT protocol using either TLS with mutual certificate-based auth, WebSockets, or HTTP 1.1, depending on how powerful your client is, your client device is, and how much cryptographic and key generation overhead that device can carry. Then on the data plane, this is where you're talking over a RESTful interface to an AWS Web Services endpoint using our familiar signature v4 authorization and authentication protocol. A lot more CPU power on this side. As I said, it's a browser or mobile device, a phone or a tablet, pretty powerful. We can deal with key generation for each session without too much overhead there, but we still want to apply those same principles of least privilege and those same fine-grained controls. And to do that, we apply policies within the AWS IoT service. These policies vary in scope. Here you're looking at control plane policies, which can be used to restrict, or rather to allow, identities, principals to perform actions via that control plane interface, which you should remember from the bottom of that architecture diagram that you saw a second ago. So you can really scope down the capabilities that are available to particular sets of credentials and build control plane interfaces that are themselves secure and operate under that principle of least privilege. And then on the data plane, you can exercise similar fine-grained control for principals. In this case, those are certificates associated with particular thing identities. And here you can scope down and control access to specific MQTT topics. So you can restrict access to both the data plane and to the control plane using a similar approach around fine-grained authentication. Managing those identities, well, as I said earlier, identities are associated with certificates, and with each certificate comes a public-private key pair to enable that asymmetric encryption that we talked about. You can generate these via the AWS IoT console. You can generate them via the CLI. And the fact that you can generate them via the CLI, well, that implies that the key generation operation is available via a web services API endpoint. And of course it is, because everything that AWS does is exposed via these web services API endpoints. And in the case of key and certificate generation, you can derive this process from the vast majority of AWS SDKs. Our CLI is built on Voto 3, our Python SDK, but pretty much every other AWS SDK also supports the same operations. So you can use this for mass scale automated generation of certificates and keys for devices, which then leads you to the next question. How do you get those keys and certificates down onto your devices? And the answer to this will vary by scale. So at the device prototyping stage, you've got one or maybe a handful of devices that you're working on. Probably they're tethered or close to your developer workstations. You can generate your keys and certificates, and you can copy or flash them and the certificate authority cert that you need onto your individual devices. It's very, very simple at small scale. In larger scale, things start to get a little bit more complex by virtue of that scale. You may still copy or flash keys and certificates onto your devices, but the numbers will increase, and you may need to work with a manufacturing partner, a semiconductor integrator, or a manufacturer to create a process to do this at scale, where you generate large numbers of keys and certificates, you ship them over to your semiconductor partner, and your semiconductor partner flashes them onto your devices together with your firmware, and that creates your device fleet. That is one way to do it. Okay, so you provide those keys and certificates to your device partner. There is another way, which I've already alluded to a little bit, which was a feature that was added to AWS IoT sometime after launch. And this is something called register on first use. I think this is a pretty cool feature, actually. This is the workflow. So rather than registering each individual key pair with AWS IoT and having the AWS IoT service generate a certificate for each individual device on that basis, instead we register our CA, our certificate authority cert, with AWS IoT. Then we sign, and we establish that trust relationship by going through that registration process up front. Then we sign all of our individual device certs with that CA cert. So when those devices first connect to the AWS IoT endpoint, they present a device certificate, and bear in mind that a device certificate contains two things. It contains the public key, which is required for encrypting data that is going to be sent back to the device for decryption with the device's private key. So it's got the public half of the asymmetric key pair in it. It also contains a cryptographic proof, which is generated using a certificate authority cert and the private key, which allows the certificate holder to prove mathematically that they hold the private key, which is associated with the public key, without actually exposing the private key. So by presenting that certificate, we enable the AWS IoT service to validate the fact that we hold the associated private key. Now, that happens on first connect. We then set that new certificate state into pending activation. and we publish a message on a specific reserved MQTT topic, which you can see there is $AWS/event/certificate/registered/ and then the name of the CA certificate ID. We can subscribe a rule to that topic, and from that rule we can invoke a Lambda function so that each time we receive a message on that topic, we can unpack the cryptographic proof, having validated the fact that the device is an authorized device, signed with the right CA, we have the right cryptographic materials. We can then attach an appropriate policy to the service, to the entity rather, and we can set that certificate state to active. And that will then allow the device to send and receive messages to and from the AWS IoT MQTT endpoint. And we've done all that without having to have prior sight of the device's public key. Okay, we've done it through establishing the trust relationship with that CA cert, and we've done it through automation, which is enabled using topic subscriptions, rules, and those AWS Lambda functions. So this is a very powerful mechanism for handling device registration at scale without having to deal with pre-flashing device cryptographic materials. Well, you've got to flash them onto the devices, but you don't have to pre-share them with the AWS IoT service before the device is deployed out in the field. All you have to do is establish the trust relationship with that CA cert, and all certificates that are subsequently signed with that CA can be activated through that process that I've described there. That's a really interesting feature of the platform in my view, one of the most important features. Okay, so we're at slide 35 now, out of around 70 slides that we're going to be going through in the course of this session, and we just got off information security, okay? And in my view, that's roughly the right balance of priority. In building IoT applications, you should be spending a disproportionate amount of time ensuring that they are secured in the right way, and in a way which is aligned and in accordance with the needs of the application that you're building, and of course the legislative or regulatory framework that sits around that app. So you can get things right by using some of these platform features. Okay, moving on, some other important things. Device SDKs. So these are the software development kits that you're going to use for building the functionality out on the things, out on the IoT devices that you want to build. And they are used to abstract and simplify access to platform features, including things like the device shadow, which we're going to talk about a little bit later. Okay, it's a very important part of the AWS IoT service. And access to the shadow is enabled by functionality that is built in these device SDKs that we provide to developers that want to build IoT products and services using AWS. These are the device SDKs that we provide today. There is a C SDK, which is ideal for microcontrollers, lightweight embedded operating systems, and that is open source and available on GitHub. There is a Python SDK, open source and available on GitHub. There is a JavaScript one and a Java one, both also open source and available on GitHub. And then we have a special purpose SDK for the Arduino Yun, which is a hybrid SDK. Actually, it has a C component and a Python API that sits alongside it. The Arduino itself is Arduino Yun rather is a bridge device where you have a component of the system that runs Linux and another component and Python, and another component of the system which is an Arduino microcontroller. They communicate with one another. It's a very good prototyping platform actually, with broad interface support and this nice abstracted programming model written in Python that you can use for access. So that's worth looking at if you're interested in that particular platform. We also have mobile SDKs that can enable you to build mobile applications that use similar protocols, use the device shadow, and use the other functionality that's available within those other SDKs that I've already talked about on the iOS and Android platform as well. Once again, you can find more information about all of these SDKs on the AWS Labs GitHub, where the distributions live, or you can take a look at the blog post there at the bottom of this slide, which is the launch announcement from the Java and Python SDKs which we launched last year, and learn a little bit more about how the different SDKs compare. You can also get support for them on GitHub, by the way, by filing issues. So prototyping. Over here in Europe, the Raspberry Pi is a very popular device for prototyping. Because the slides are available, I've packaged up some resources here that Raspberry Pi developers can use to learn more about prototyping on the Pi. There are also some really excellent starter kits available on Amazon.com or other local Amazon properties, depending where you are in the world, that can help you get hold of some of the electronics that might be helpful in building sensor arrays, switches, and other input into prototype IoT devices on the Raspberry Pi platform. There's also a Sense Hat available, which is a prepackaged set of sensors which can be used to build some fun applications. It has an 8x8 LED matrix on it, and it's a good fun product for developers to experiment with, which I found very popular in some of the hackathons that we've run over here. Getting started, you need these things. So you've got to build the wiring Pi module for embedded C. If you're going to use the Python SDK, you need the wrapper for that. That will enable you to control the GPIO interface ports, pins on your Raspberry Pi and interface with the different sensor packages you could get. And then for the Sense Hat, there's a standalone Python module for that, and that's only available for Python at the moment. So if you want to work with the Sense Hat, you really have to use the Python SDK. Downrange a little bit into the microcontroller based approach with the Arduino and other similar platforms. We actually have a set of hardware partners that have pre-packaged the AWS IoT SDKs of various types with microcontrollers. They provide getting started guides, a compatibility statement, and a port of the CSDK in most cases onto their hardware. So you can take a look at these, mostly available on Amazon in the US, particularly in the US on Amazon.com. Some of them ship globally, but particularly well available in the US. And if you just jump onto Amazon and search for AWS IoT Starter Kit, you'll find a selection of different options there. Very good for prototyping. And if you read the documentation that comes with many of these kits, you'll find that the manufacturers, some of their business model revolves around helping organizations get from prototype to production with electronics products. So if you're building on the MediaTek, for example, or you're building on the Marvel or on the Microchip, you can work with those vendors and they will productionize, package up a custom-built interface board and microcontroller for the specific application that you have in mind. So if you do want to build a product or build a solution within your own organization using IoT, you can take a look at the starter kits as a mechanism for doing that, and you've got an opportunity to work with some of those vendors to take prototypes that you might build through into large-scale manufacturing, which I think again is quite an interesting aspect of the AWS platform. So we've got our security, we've got our prototype. How about sending and receiving messages? And to make that easier, we provide a fully managed device gateway. This is a fully managed MQTT endpoint, and each AWS account will have one of these for each AWS region around the world where AWS IoT is available. You'll get a unique DNS name for your endpoint, which you can view within the AWS IoT console. You configure that within the Device SDK that you're using, and you can send and receive messages to and from your private endpoint, which is specific and private to your own account. It will have its own certificate, its own public-private key pair, and your devices will communicate with that particular endpoint in each specific region that you want to work within. The major benefit of the endpoint is that it's a fully managed elastic service. You can send and receive messages at any scale, and AWS will take care of the gateway capacity to enable you to do that. In the US East 1 region, we will charge you $5 for every 1 million messages that you send through the gateway. There's nothing to deploy, nothing to scale, nothing to manage failure conditions for, nothing to get paged at 4 in the morning for when it runs out of capacity or breaks. We deliver that as a fully managed service as a component of the AWS IoT service. If you're not very familiar with MQTT, this is a protocol, and I've already alluded to this a little bit actually. It's extremely popular in low power, lightweight device contexts, and the main reason for that is connection efficiency and battery efficiency. And you'll see some numbers there. It's 170 times lower power than receiving messages over HTTPS, and this is by virtue of the TLS mutual auth approach with the pre-shared keys that are used. That is a really efficient way of handling cryptography and handling data transport without having to resort to per session key generation, and the protocol itself is also more efficient. And as I said, we provide that scaling capability. We have customers using the gateways, using the message broker at extremely high volume. We just scale it in accordance with the level of volume that you have, and you have nothing to deploy and plan, as I mentioned earlier. So once you've got your devices connected and you're sending and receiving messages to and from MQTT topics, which is what we call the pub-sub collections within the MQTT protocol, you probably want to route those messages and do something with them. And for this purpose, we have the AWS IoT rules engine. When you are sending a message, what you are going to be sending is a small block of JSON that includes device attributes, for example. It might be a shadow state update, which I'll come to in a second, or it might be a message. So you've got a thermostat, a connected thermostat. It might be a message which says the temperature is currently 41 degrees, for example. So what do I want to do with that? Well, I want to evaluate the contents of that message, and that's the role that the rules engine plays. You can define rules within the rules engine that inspect the contents of the messages that are coming from your devices, and they operate upon the messages on the basis of the content. And that operating can be forwarding messages, it can be storing messages, it can be transforming messages, it can be republishing messages, it can be integrating with a variety of different AWS services. You have a lot of different capabilities that you can use here to build the rich functionality that you probably want to build if you're going to create really rich and capable IoT applications that have a lot of value. Okay, and this capability comes from the fact that an SQL-like language construct, SQL-like syntax, is used in the gateway. So you can select on the basis of topic filters, you can use where, you have support for advanced JSON, there are built-in functions, mathematical operations, you can add data which can be generated at the gateway connection point, such as timestamps. You have a lot of flexibility here to manipulate and forward messages on the basis of their content, and that allows you to build rich applications from the very simple, like switching lights in the basis of messages that you receive, through to the much more complex, maybe controlling systems like irrigation systems with embedded logic that are built into your rules using IoT SQL functions. You can find all of those documented if you visit the URL at the bottom of the slide here, but you can see you have the capability to do substring selections, to do replacement, to do republishing, to dynamically add attributes like the MQTT client ID that you can see being dynamically added here at the point at which the messages are received by that gateway. That could equally well be a timestamp, as I said earlier. So you have a lot of power to manipulate and modify messages on the basis of their content, plus the logic that you choose to build. And the gateway, well, you can do complex evaluations, so you can respond to large numbers of messages on the basis of patterns. But B, you can also take multiple and simultaneous actions. So you're not restricted just to doing one thing. You know, you can trigger a Lambda function, you can persist data in a database for long-term analytics or visualization, and you can also send a push notification to a mobile app. And you can do all of that from one rule on the basis of the evaluation of one message that has come from one device, or on the basis of much more complex evaluations that you might create using that SQL-like language. This is a very powerful tool for building application functionality in a way which, once again, doesn't require you to operate anything. You know, we run the gateways, we scale the gateways, we run the rules engine and scale the rules engine. All you have to do as a developer, as a product builder, is define your logic. We do the heavy lifting that's required to turn that into functionality in the platform. So I said you can republish messages, you can persist them, and the way that you can persist them is by integrating with other AWS services or third-party services via that rules engine. So one of the actions that you can set up is to forward a message to another AWS service. We have a large and increasing number of services that are supported via the rules engine. So S3, DynamoDB, Kinesis, SNS, Lambda, SQS. We support a service called Amazon Kinesis Firehose, which enables you to take a Kinesis stream and persist that data in S3, Redshift, or EMR. So you have a really strong capability to integrate with a variety of other AWS services, and we're constantly adding to this as well. We recently added the capability to store messages in an Elasticsearch cluster. You can combine that with Kibana to build simple visualization dashboards for your AWS IoT control plane to enable you to monitor and manage applications that you're building. You can forward messages into the AWS machine learning service, into Amazon Machine Learning, and you can use that to make predictions about data that might be missing from from data streams, so you're constantly receiving, let's say, temperature or humidity information. You miss one or two reports because of a network issue. You can suggest what the most likely values are for those missing pieces of information using the Amazon Machine Learning service, and there are obviously other services there that are integrated as well. So this is how the richness, the features, the functionality that customers want to build into their IoT applications can be built using a collection of different AWS services. And that really helps you, once again, minimize down the amount of heavy lifting that you need to do in building IoT apps. Next area to talk about is storing and querying device metadata attributes. Many customers, well, they want to store information about devices which is static in nature but might be used for management or monitoring or maintenance of a fleet of devices. Okay, and the AWS IoT Thing Registry is a platform component that we have that enables customers to do this. It's a document database under the covers with a set of interfaces that are built specifically to make it simpler for customers to store and query metadata about physical devices, about physical things that might be connected to the AWS IoT service. Just by way of illustration, illustrating via the AWS CLI, once again illustrating that there's an API, web services API, that exposes this thing registry to developers. You probably wouldn't use the CLI for this at scale, but of course you can then go on to use one of the other SDKs that we support, whether that's JavaScript or Python or Java or C#, whatever you want to use. You can create, query and list things on the basis of device metadata that you've chosen to store about them. You can also create types. Okay, so you can create prototypes for particular classes of thing and define some or all of the schema that is required each time you create a thing. The thing registry simplifies down the process of creating metadata stores associated with physical devices. And you can create classes or thing types which are prototypes for connected devices that you want to maintain in the system. So here's an example of creating a thing prototype, a thing type associated with light bulbs, where we're specifying a couple of searchable attributes, and then your developers could use that as a basis for creating devices, and those will be mandatory attributes that were required for each new thing of that particular type they chose to create within the system. Again, it's just offloading more of the heavy lifting associated with IoT application development. That's a quick discussion of device metadata. Two things left to cover. We've got about 15 minutes. So the device state cache, this is the AWS IoT Thing Shadow. And I actually had a very interesting conversation with a customer in the UK, British Gas Hive, part of Centrica, one of the largest energy retailers here in the UK. They have a whole suite of products associated with the connected home that they started with connected thermostats. And they actually built this themselves in the first iteration of their product, which predated the AWS IoT service. It's an essential component for many IoT applications. And if you come across IoT developers that have built their own services and haven't used platforms, this can be one of the most commonly repeated activities. So what does the Thing Shadow do? Well, it allows you to asynchronously read and set device state. So my device might be some sort of device which is periodically connected to the network. It might be a device which is power constrained and therefore is only powered on and active for a certain percentage of the day or week when it's required to do so. But I might have an application which is asynchronous, which is driven by human beings, where human beings might want to get an update on the status of that device at any time, even when it's not actually powered up or connected to the network. So the Thing Shadow enables you to do that, and it enables you to do that in a way which is driven and scheduled and initiated from the device. So you would have a synchronized shadow method present in the Device SDK, and that's present in all of those AWS IoT Device SDKs that I covered earlier in the session. And you can call that periodically, and when you call it, it will synchronize the state of specified data structures held in the device with the shadow. You can then come along asynchronously and query the device state from the shadow, and you'll get the last reported state as it was pushed from the device to the shadow. The cleverer part perhaps, is that you can also do this in the reverse direction. You can, for example, this example here with the mass spectrometer, you can set the desired state of the device via that REST API on the async side of that shadow, and the next time that the device calls sync, that synchronization activity will be bidirectional in nature. So it will receive the latest update from the shadow and push its latest update to the shadow. And there is versioning and conflict resolution built in to enable you to deal with conflict and version issues there. Okay, and it works like this. So we've got the offline capability. The Device SDK, well, it abstracts this from the device developer. So you don't have to do this stuff that you're going to see on the slide in a second. All you have to do is call the synchronized state capability within the specific Device SDK that you're using. The device will then publish its current state. It will persist that in that JSON data store within the AWS IoT service. Applications can request that and they will read it out of the data store. They can change the state and that will update that data store. And the next time you synchronize the shadow from the device, you'll get the updated state back from that data store. And you'll publish your run state back from the device to it, as I mentioned. So it's a very simple built-in feature for building asynchronous communications capabilities into IoT applications. It's actually one of the most popular and heavily used features of the AWS IoT service. And the reason for that is it's so simple. Under the covers, you're using special reserved MQTT topics. So the same low power, same strong authentication, same strong device identity, same fine-grained access control. That's all in play, but you don't have to worry about that as a device developer. You're just dealing with that shadow method, shadow capability within the SDK that you choose to use, and all the complexity is abstracted away from you. You can see it in the console, and of course you can write your own code which manipulates with the shadow using the familiar AWS Web Services endpoints that you're used to, using the vast majority of the SDKs that we provide. So it's perfectly possible to manipulate AWS shadow state from iOS or Android applications that you're developing using those SDKs, web applications that you might have running fully in the browser that run in JavaScript, or using web services that you write in Python Flask or Express or other frameworks using the respective SDKs in that context as well. So it's a really popular feature of the service. Last thing to talk about, this is upcoming. So something else that we heard from customers actually, edge computing capabilities. So there are challenges with certain types of IoT applications, certain types of context for IoT applications actually introduce challenges. Things like resource extraction, military use cases, agriculture, manufacturing, maintenance, where the devices themselves may be in locations where connectivity is either not available, it's highly constrained, or it's very intermittent in nature. So things like subsea applications or mining would be a really good example of this. How about an ROV, remotely operated vehicle that you're using in the oil industry, maybe to perform subsea welding or equipment inspection, and that device has very poor latency, or very intermittent connectivity, or bandwidth to it is extremely expensive, but you want to control devices on that subsea piece of plant using the same programming model and the same kind of logic and capabilities that you might use in a permanently cloud-connected, rich IoT application. How can you go about building that? That was something that customers were asking of AWS. Could we produce a service which would make it simpler to support that kind of use case? And in response to that, we announced a preview at AWS reInvent in December last year of a brand new service called AWS Greengrass. And this is a binary deployable, so a piece of software that you would install and run on the ARM or Intel platform, and it's intended to be deployed in these semi-disconnected or disconnected environments. It provides local compute, secure communications, local data caching with a local shadow capability, and local messaging through a local MQTT gateway. It uses the same programming model, the same deployment model that you would use for AWS IoT, but it's going to be built into devices at manufacture. All the Greengrass runtime will be installed onto gateway devices that you might choose to own and operate as a component of an overall IoT service, an overall IoT solution that you're looking to build. So this is a service that is currently in preview. If you can see use cases for AWS Greengrass within your organization, maybe you're producing smart home products or connected agriculture equipment, or you have a manufacturing resource extraction or maintenance use case where you think this kind of capability could be valuable for you, you think it could potentially be useful for you, I'd really encourage you to talk to us about that. We are admitting customers into the preview right now. I am aware of several customers, even here in Europe, that we're working with on preview activities at the moment, and we would love to have more customers, more use cases, a better understanding of how customers could potentially deploy this service and make use of it. So if you are in that situation, please let us know, communicate with us, talk to us, and let's see how we can collaborate and get Greengrass into your organization in preview and establish whether or not you can make use of the product. Okay, so that's all the content for this session. I often talk about resources at the end of these sessions. If you do have a desire to learn more, you want to follow up, you want to access the SDKs, you want to read the documentation, you want to log into the AWS IoT console, maybe try prototyping with some of the devices that I've talked about. All things to do with AWS IoT are available here, awsamazon.com/IoT, so you can find many, many more resources there. And you can always contact me as well on Twitter if you have questions or follow-up, and I will help you. So I'm going to turn the floor back over to our host now. I think we're going to take a few live questions, but back over to you. Thank you.
Thanks, Ian. Great presentation so far, and we'll continue to answer any questions as they come in. We're now going to switch over to the live Q&A portion. On your screen, you will see 4 polled questions. Please give us any feedback that you have here. Additionally, continue asking any questions that you may have